All right, so we talked about 5, our trigonal bipyramidal, but now we want to say, what if I want to add a 6th? Okay, so here's my 5, 1 above, 1 below, 3 in the base. So if I add another one, I can't really add above, because there's already one there. Can't really add below, because there's already one there. So he has to go in the base. So instead of it being 3 in the base, now I'm going to have 4. So instead of having a triangle, what shape has 4? A square, okay? So this guy's going to go up. This guy's going to go up. He's going to go underneath. So I'm going to have a square. So you've got, let me hold it like this so you can see it. So here's my 4 in the base, and if I tilt it, you've got 1 on top, 1 on bottom, and then my 4. 1, 2, 3, and 4. Okay? So that would be my 6. All right, so let's look at that. Now, let's see what the name is. You might think, okay, what makes a square pyramid? Is it square bipyramidal? No, okay? That would actually be kind of easy, but that's not how they did it. So this one's a little funky. If I have 6 of them, this is called AX6 because I have 6 things, and it actually is called an octahedral shape, okay? I'm gonna go ahead and go to this slide real quick so you can see it. So this is the octahedral shape. And so what it means is you have that square base, pyramid on top, pyramid on bottom, but it's an octahedra because it has 8 sides, 8 faces. Here's a face, here's a face. You can kind of see it like here. Like here's a face, here's the face, here's the face, here's the face, that's 4. And then you have the 4 faces on the bottom. So you get 8, 4 on top, 4 on bottom, 8 faces of your hedron, and so 8 prefix is octa. So that's why it's called an octahedron, because it has 8 faces. Okay, so this is going to be an octahedral shape, okay, because it has 8 faces, 8 sides. Now, here's the important thing. All of these positions are equivalent. There's no equatorial axial, because if I turn it, here I have 4. If I turn it, still have 4. If I turn it this way, still has 4. Okay? Because no matter how way I turn it, I'm always going to have 4 in the middle, 1 on top, 1 on the bottom. So they're all equivalent, no differences. Let's talk about the bond angle. So from the top position to the side, this is 90. Now let's look at my my square, sorry. If I look here at my 4 from inside the square, this is also 90. So doesn't matter if it's equatorial to equatorial or axial to equatorial, it's all the same because all I get is 90 degrees, okay? They're all equivalent. So here you can see if I put my balloons, you got 1 on top, 1 on bottom, and the 4. So from here to here is 90, and then here is also 90 within my 4. So here you would have your central atom here, 1 on top, 1 on bottom, and then your 4. Okay? So this is what it would look like. Here's your Lewis dot picture. You'd say 1, 2, 3, 4, 5, 6 electron groups. So this is what it would look like. 1 on top, 1 on bottom, and 4 in the plane. And top to side is 90, and within is also 90. Okay? So that's our octahedral geometry. Here's one more picture so you could see kind of our 3D modeling with our ball and stick model, and then our space filling model, just to give you an idea of what it looks like. All right, now that was our 6 parent groups. Okay, so we said if there's if there's one thing on the central atom, it's linear. If there's 2 things on the central atom, linear. 3, trigonal planar. 4, tetrahedral. 5, trigonal bipyramidal. 6, octahedral. Those are my 6 parent family groups. What that means is they don't care if these are lone pairs or if these are bonds. Okay, so this is kind of my big parent geometry. And so they just want to know how many things, lone pairs, electron groups. Lone pairs, bonds, how many's on there. The next one we're going to talk about the molecular geometry. Okay, so this was the electron geometry. The molecular geometry cares if these are lone pairs or if these are bonds. So these are going to be subgroups underneath that parent geometry. Okay, And so in the next lecture, we're going to talk about what happens when it's a lone pair here instead of a bond.